So Erik is assistant professor, University of Amsterdam, in part of the Amsterdam Machine Learning Lab. He's recently been awarded with a Veni grant from the Nederlandse Organisatie voor Wetenschap. No, I shouldn't say that. Wetenschappelijk Onderzoek, right? It's the Dutch Research Council, and also has been awarded sort of with a Young Researcher Award at the MICAI 2018, if I'm correctly informed. And he's going to talk today about group equivariant CNNs beyond roto-translations, B-Spline CNNs on Lie groups. I'm definitely looking very much forward to your talk.
Okay, thank you for the introduction. I think you can see my screen and the pointer as well.
Yeah, that works really well.
Great. Let's minimize this on my screen. Yeah, okay. Yeah, thank you for the introduction, and also thank you for the invite. I actually decided to change the slide a little bit. So I will be focusing mostly on the group equivariance part. I think that's a very important thing, and basically this is like a promotional talk for group convolutions. But I want to place this in a recognition by components context. So I want to do this talk a bit tutorial style with a lot of explanations and visualizations, and this helps me a lot, and I find it a nice interpretation of things. So the context will be like this. So I'll start off with the motivation for why do we want to work with equivariant learning models. And once that motivation is established, I move more towards the mathematical part of things. So I describe the prerequisites, like the group product and the representations. And then I come to group convolutions, which I place in the context of pattern recognition by components. And once that is done, I show with some experimental examples that, well, GCNNs are actually very relevant and they work very nice. And yeah, because this is a mathematics symposium, I felt like I should include at least some theorem. So if you're thinking this maybe is too much applied, that's something nice to look forward to at the end of this talk. Yeah, so let's start off with the motivation. So in a lot of applications in practice, one has to deal with notions of invariance, right? So if I have a cell and I want to classify it as healthy or pathological, I want this classification to be independent of the rotation under which this pattern appears, right? A cell is a cell if it's rotated or not. And currently, like classic methods do not necessarily provide that guarantee. It might even say the exact opposite. So a common approach to deal with is to rely on data augmentation. So you make rotated copies, you keep the training labels fixed, and you let the network figure out how to deal with this invariance property. And this obviously still has some issues. Well, for one, we still don't have an actual guarantee that the network is invariant under these instances. We just hope that it learns to figure out this property. But I think most importantly, valuable network capacity is spent on learning invariance. Whereas invariance and equivariant is actually a very well, nicely understood geometric thing. And it seems like a ways to let the network figure this out because these trainable parameters, they could be better spent on learning core representations of the data. So data augmentation results actually in a lot of redundancy in feature representations, and we want to avoid this. So bam, the solution is group convolutional neural networks, and I hope to convince you of that in the upcoming slides. Okay, so so that's about invariance, but equivariance, that's even maybe a more important property. So equivariance in the case of translations really means that if I translate my input, my output translates accordingly. And this is important because it ensures that no information gets lost. It's just moved to different locations in the image. So no loss of information is key here. But also this equivariance property enables weight sharing across different locations. So a pattern here may look the same as a pattern over here. So we can reuse these kind of patterns that we learned well, for weight sharing, basically. So that is actually one of the main driving forces behind the success of CNNs. We also know that convolutions are not rotation equivariant, or generally not. And so that when the input rotates, it leads to a distortion in the output. So we get different responses, and we have to deal with that. Okay, so in summary, the importance of equivariance is that no information gets lost when the input is transformed, but also these notions, they provide a guarantee to deal with transformations on the input. So we know what happens in the output domain. And so basically I'm going to focus on group convolutions because they provide actually ways to provide equivariance beyond just translations. They provide geometric guarantees, and it increases weight sharing. And the idea is that generally, for example, in computer vision problems, which is not an invariant problem, because generally we have a horizon, we have people in upright position. So the problem itself is not invariant, but we want to increase the weight sharing in an equivariant way, because we want to detect lines and blobs at all possible rotations and scaling. We want to reuse these representations over as much symmetries as possible. So we want to do maximal weight sharing, and that's also where group theory is going to help us. Okay, so that's a motivation more from the properties that we desire such a neural network or deep learning system to have. But what always intrigued me is how we tend to think of objects being composed out of lower level components, and this is what I call recognition by components. There's actually a nice field of the psychology of vision concerned with this. The idea is that look at this heart or medical image data, we tend to, for example, define or detect surfaces locally, and they can appear in their arbitrary rotations at several scales. So they appear all over the data. And if you place them in a particular configuration, so key is that you place them in a relative configuration, then it forms a tube, for example. And this tube again appears in the different poses, whereas the relative configuration stays intact. And this can again be used to define higher level features. And so this idea of relative information relative to this pose, I see a surface there and there and there. This idea of relative information processes, in my opinion, is what group theory is all about. And I'll give some examples of that later on. Yeah, so that's one part of the inspiration. And the other thing is that if you keep monitoring what's happening in the deep learning landscape, there has been quite some attention to capsule networks, which are driven by this very same idea. And today I try to put this into a more group theoretical context. Okay, so that's for the motivation. So now let's go to what we're actually talking about. So let's make things a little bit more formal, such that we're all on the same page. So what is a group? So a group is really a set of elements together with a group product. And this group product is a binary operator that satisfies some axioms. Most importantly, that if I have two of these elements of the group and take the group product, I am again obtaining an element in the group. So that's closure. And as for other axioms, it satisfies. But let's go to an example. So the translation group, it's a somewhat trivial example. So it's composed of the set of 2D translation vectors, and it is equipped with the group product defined as such. So two translations combined give a new netto translation, which is the sum of these translation vectors. And that is visually depicted here. So this netto translation is obtained by looking at the product of these parameters. And now, really, there's no really need for going to group theory in this case, because we see combining that is just adding the vectors. So we're still dealing really with the vector space structure here. But when we go to the group of roto-translations, then things get a bit more intricate. So in this case, the space that we consider consists of translation vectors and rotation angles, or equivalently, really rotations denoted with SO2. Yeah, so that's a space. And now we have a group product which says, okay, if I have one translation and another with a rotation, if I combine it with another translation, another rotation, I obtain this netto roto-translation. And we see an interaction taking place of this rotation part on the space. So there's a coupling taking place, and that's actually denoted by this semi-group product indicator. This really shows that I really have to rely on the group product. I cannot just add translation vectors and add rotation matrices to get my new transformation, because that doesn't make sense in this specific context. So really I need a group structure to define how two roto-translations give me a new roto-translation. Yeah, so I think it's good to think of these groups in this presentation mostly with elements that describe parameters that describe a transformation, and the group product basically tells you how to combine these parameters to give a netto parameter. I'll give some examples more later. Yeah, then there's all sorts of groups, and maybe the main point I want to make here that I'm mostly concerned with groups that consist of a translation part together with some other subgroup. In this case, scaling, could be rotation, could be an affine transformation. But I choose this structure because mostly we're concerned with signal data, like images or audio waveforms, and then some symmetry which we're interested in. And then combined, they define a group product where there is some interaction of the scaling part taking place on the translation part. Yeah, so that's all I want to say, I think, about this slide. Okay, so now we have made some definitions, and let's go back to this recognition by components part. So put that in context. So now I want to describe patterns in terms of this group theory. And this is a first example. Like we can think of a phase being composed out of local orientations, here indicated with these arrows. And we can treat this as a set of group elements because we can always choose the identity element, for example, the nose, and we can roto-translate it to the eyes or to the other points. So we can say that the phase is really composed out of a set of local roto-translations. Yeah, okay. And so these elements, they represent, for example, line segments. Now, if I want to know what this pattern looks like in another point, for example, G, then I simply multiply everything on the left side with G. And so basically that transforms every element to this new position. The nose is now aligned over here. And this relative configuration stays the same. So the only thing I need to know is the group product, and then I apply it, and this moves my representation around. Now, so now I want to translate this to group convolutional neural network. So I talked about a set of points, but now I want to talk about convolution kernels. Sorry, let me just mute this. Okay. Yeah, so on the left-hand side, we have this collection of parts in certain poses. So these are group elements. And on the right-hand side, I think of my pattern as a convolution kernel. It's a function that assigns weights to relative positions and yeah, or relative positions and orientations if I go to a different group. Yeah, so if I want to transform these patterns, for example, in a pattern matching framework, this pattern transforms via the group product, and this pattern transforms via representations. So this is actually a last definition that I'm going to make now to be formal. So we have that okay, so what is a representation? It really is a linear operator which acts on some vector space, could be infinite dimensional, and it is parameterized by a group element. And it's called a representation if it satisfies the group structure in this way. So a concatenation of these two operators can be described by one netto operator, which is parameterized by the product of these two group elements. Yeah, so that's visually depicted over here. And there are all sorts of representations, and I'm mostly interested in the left regular representation. That's one of the most basic examples. And then this representation is really induced by the action of the group on the domain of which this function lives. So the transformation of this function is really just the same function, but with the domain shifted via some transformation. Okay. So now we have all the ingredients in place to start defining group convolutions. So let's do that. So let's take a look at group, well, correlations actually. So they're the same as convolutions with a reflected kernel. So a cross correlation is defined as follows. Really, we have a shifted kernel and we take an inner product with our input image or input function. So if we then describe this in terms of representation theory, we say we're taking inner products of our kernel, which is transformed under the representation of the translation group, and we take inner products. So this is a template matching. So this is our base pattern, this is our image, and we're going to translate, and every time we take an inner product. And whenever this pattern matches the data, we get a high response. So this is the main mechanism behind convolutional neural networks, right? That we have a whole set of convolution kernels, And then the deeper we go, we keep applying these convolution or correlation operators. Now, we know that the convolution or correlation operator is equivariant, and this actually directly follows from the fact that the correlation operator can be defined in terms of this translation operator, and then it's relatively straightforward to show that this commutation diagram holds. But generally, this doesn't hold for rotations, for example. And actually, we can make this diagram work if the kernel is isotropic, and that's a remark I'll close off this talk with. But generally, this doesn't hold. And basically, that's due to the fact that we have a mismatch of this representation and representation in the operator, the correlation operator. So now it seems pretty intuitive and straightforward to just replace that operator, this representation, with that of the roto-translation group acting on 2D images. Yeah, so that's what we're going to do. So we let the group SE2 act on 2D images, where the kernel is my 2D image in this case. And because we're dealing with a semi-direct product group, I can split this in a rotation and a translation part. And that's actually why I like semi-direct product groups, because computationally, numerically, this makes things much easier. And then this whole thing basically is represented by a rotation of the coordinates and a shift. Okay, again, an illustration. So this is my pattern, which I'm matching in the image. So I'm convolving it. So I rotate it. So that's the representation of the rotation group. And then I translate it by the correlation operator. So whenever there is a match, I get a high response in this field. So this operator, which I call a lifting correlation, turns a 2D image into a function that lives on the group. So a 3D image, which assigns values to local positions and orientations or rotations. So it decomposes this image into patterns, such patterns, and but basically assigns the presence of such patterns in the data. And because now we defined it via this group representation, it's again quite easy to show that we have this commutation diagram where a rotation on the input actually corresponds to a shift twist of the output, because the vertical axis now encodes for rotations. You see, if we rotate the data, everything is shifted along this axis. Okay, sorry, there's some messages coming in which I cannot close off at the moment, so I apologize for that. But yeah, let's just continue. Okay, so now we basically generalize the correlation operator to what we call a lifting group correlation. And also in subsequent layers, now we have to deal with functions that live on the group. So the only thing we need to know is how to transform these kind of functions. So we use the representation of the roto-translation group on functions that live on the group. And the form stays exactly the same in this template matching framework. So we have a kernel which assigns weights to local rotations and translations, and we transform it by the rotation group. And then we match the image for this pattern. So that means in the end, we pick up at one point we have a match of this pattern corresponding to this smiley face at orientation 0. And when the pattern is rotated, obviously we get the same response, but now shifted to the corresponding rotation layer. And again, this commutes. So basically it means that the rotation on the input corresponds to some transformation on the output space. Okay, so in summary, so we started off with a cross-correlation operator, which we regarded as taking inner products with a translated kernel, and then we simply replaced the operator that we applied to this kernel via a group, well, via a group representation, in this case a roto-translation group. And this generates a higher dimensional object, and of course here we can again define such an operator. So again, going back to this recognition by component framework, so we have an input image with in which some patterns appear, like faces consisting of local orientation, and the lifting convolution decomposes this into these smaller parts. So a face has all these local line segments. And then group convolution kernels are 3-dimensional. They assign weights to a relative configuration of points. So I want to see an eye over here at this orientation and a nose over there and so on. So these are 3-dimensional group convolutions. And well, so they basically turn lower level parts into a higher level thing. And if we, in the end, we're not interested in, for example, what orientation we saw the face, we can simply project over this rotation axis to make the entire pipeline invariant to rotations. So then you end up again with a 2D feature map, which only indicates the presence of a face and not necessarily also its rotation. Yeah, the same principle can be extended to the other type of transformation groups. For example, we can think of a face being composed of circles at different scales, and that induces a particular pattern in these lifted maps. All right, yeah, so let's go to some experimental example. So here the task is we want to classify a cell as either a healthy or pathological, so a mitotic cell. And this is the general recipe. So we start off with a lifting convolution, and okay, and then all these group convolutions. And this makes sure that this entire pipeline is equivariant. So if I rotate the input, all information stays in the network. It's just shifted to different locations. And then in the end, we end with a projection layer to make the task fully invariant. So let's go to an actual example. So here we feed an image of a cell. We have a lifting convolution kernel, which is applied under different rotations. And each rotated version picks up certain structure. And we stack them, and this generates our function on the group. So we see that a particular amount of information ends up, for example, over here. Then we apply group convolution layers to get more and more abstract representations. And then we get a feature vector. So let's say the spatial axes are reduced to 1 point. These are the channels, or the multiple responses, and this is the rotation axis still. And now if we take the projection over this rotation axis, I get a response with this, which is invariant over rotations. So we can verify that this works by just feeding a rotated copy of this thing. And we see that the same information is being picked up. It just ends up at different locations in the data or in the network. And then if we project it, we get exactly the same response. So this is nice. Group convolutional networks can thus be used to construct very abstract representations, which are invariant essentially to a particular subgroup. Okay, so now we start building these networks and experimented with it. So basically what we first test is how does this compare to data augmentation? And to explain this plot a little bit. So n represents the number of rotations that I sample. So it specifies the discretization of the rotation group. So ns1 means really no rotations at all. So this is a 2D CNN. And then we sample orientations of rotations in a 180-degree interval, 90-degree, and 45-degree. So this is really a proper group convolution, or at least with a proper discretization. And then all this is without data augmentation. And then on the left side, we actually have a 2D network with data augmentation. So basically, we saw that with a group convolution, we get very stable results, and we start to outperform classical CNNs, which do rely on data augmentation. And the fact that we're able to surpass it actually comes from the fact that our model does not need to spend weight on learning invariance properties because it's equipped with this geometric structure. So it can focus entirely on learning relative feature representations. Yeah, another remark I would like to make is that group convolutions consider both local equivariance and local rotation patterns, whereas data augmentations typically only address global transformations. So there's also an advantage of group convolutions over data augmentations. Then we looked at the stability of these methods. So basically what this plot shows is for every rotation of this input patch, it shows the probability of it being a healthy cell. So red is really a group convolution, green is a 2D CNN, and blue is with only 90-degree rotation angles discretization. So you see that the group convolution is very stable. It always gives the same prediction, whereas for the other methods, it would say for one rotation it says it's healthy, and for the other one it would say it's pathological. So this is nice. We experimentally showed that GCNNs are much more stable with respect to such transformations, which of course we theoretically expected. And finally, we show that GCNNs are more data sample efficient. So basically, if I look at this, these are group convolutions. Let's take a look at the blue curve, which is a network trained with only 25% of the data. And if we match it with the 2D baseline, we see it still significantly outperforms networks, 2D networks, that are based on 100% of the training samples. This, of course, has to do with the fact that if there are symmetries in the data, the GCNNs only need to see one instance of a cell, for example, and then knows how this looks like under different rotations. Yeah, okay, so we tested this on several applications and we see similar patterns appear. This is recent work, and I'm quite excited about this because up until recently, not much work has been done on scale equivariance. And this actually has to do with the fact that numerically, or if you start implementing this, you run into all sorts of problems. And theoretically, the most concerning problem is the fact that once you discretize the scale group, it's no longer compact. But that's an issue which I wrote a paper about how to deal with this. But basically, we showed that, again, also with these kind of groups, with the idea that we have patterns at different scales relative to each other, I showed that also here with GCNet, you can get the performances which you simply cannot get with data augmentation or other multi-scale heuristics. Okay, so yeah, I'm quite excited by GCNNs. Big fan, as you can tell, probably. But I'm not the only one. So there's a large body of literature, and this is ever growing, of papers that address this from a theoretical point of view, but also experimentally. And all results are in line, which is, of course, theoretically to be expected. Yeah, so basically, GCNNs provide geometric guarantees. It provides performance gains that cannot be obtained with just data augmentation, and they have increased sample efficiency. Now, I wanted to put this a little bit in context. So group equivariant techniques are actually relatively common in the classical computer vision field, and probably also in quite some other fields, in physics, for example. But in the deep learning landscape, I would say it really, this paper by Taka Cohen and Max Welling really kicked off this research line within the deep learning community. Basically, what they did in this paper, they described a quite general theory for group convolutional neural networks, but then they only experimented with discrete groups. So they work with images live on a grid, and this grid has certain symmetries, like 90-degree rotations and flippings. So they built GCNNs for this kind of data. And then subsequent work focused on extending this to larger discrete groups. So either going to higher dimensions or change the discretization. For example, this works with a hexagonal grid, allowing for 6 rotation angles. But of course, other in parallel methods were being built to translate this to continuous group convolutions. And what's actually most interesting about this is that almost exclusively they all basically focus on rotations, so rotations and translation. And this is the idea behind this is, of course, that if you go to a continuous setting, then you want to work with basis functions or interpolation methods, but typically basis functions which are continuous and which have a discrete set of coefficients. And if you work with rotations, then spherical harmonics are super convenient to work with. And that's what most of these methods are built upon. And it comes with a very rich and nice set of representation theory. But these methods do not generalize well to other type of groups, like general Lie groups, scaling groups, and things like that. So recent work has been focusing on moving away from these spherical harmonics, but also consider other type of basis functions. And I'll give a comment about it in a minute in this recent paper. Okay, so that's one line of research. And then we have gauge equivariant CNNs, which is also a really interesting topic that basically tries to move one step further and says, maybe I'm not interested in defining my equivariance of the entire domain as a whole, but analyze things locally and work with the gauge frame. So I attach to every point in my data a frame, and I know how to connect these frames. So that's the main idea behind gauge equivariant CNNs, and that allows actually a further abstraction of GCNNs to other type of data structures. Yeah, okay. So basically today I talked a lot about images, but these methods, and I think I would definitely like to point out this paper by Vinci et al. Depicted over here, they showcase actually quite a lot of other applications, from molecular data to more abstract things like dynamical systems and so on. And so these group equivariant machine learning settings, they extend beyond image data, of course. Okay, because the talk was originally going to be about this paper, I want to have some remark about it. So I said I'm moving away from these spherical harmonics basis functions, and I did so by actually defining basis functions on the Lie algebra instead of the group itself. So there is a mapping from a point on your manifold to this tangent space by the logarithmic map, which has a flat Euclidean space. And then I can start defining B-splines, which are very well known in computer vision and maybe some other fields as well. And they have very nice properties, such that, for example, they're localized, they can be deformable. And so that's actually part of my current research, to explore these kinds of properties from a more also experimental point of view. Okay, and then, wait, I want to move back to, sorry. Okay, never mind. No, yeah, okay, so I really wanted to show that now we can go beyond applications where rotation symmetries are important and also consider scale. And we did that, for example, in some audio processing cases, where we reach really nice results as well. Okay, and I promised I would end this talk with a theorem. So here it comes. I'll formalize it in the next slide. But the idea is that all these networks, they're still instances of a neural network, but it's just that they're placed under equivariance constraints. And this turns out to be a very good inductive bias. So if there is structure in the data, we want to use it. And that means we have to put equivariance constraints, and that leads to group convolutions. So basically, you can show that every linear map between feature maps, which is equivariant, has to be a group convolution. And maybe to some of you, this might be quite common, but I find this a very important statement. And so let's take a look again at classical neural networks. So we have an image. I personally would like to treat it as an image, but let's just treat it as a flat vector. And a neural network just moves from representation to representation via these mappings. And the main component here is this linear map, which is really just a matrix vector multiplication, and you want to learn the coefficients. Okay, so that's the vector interpretation, but now I'm working with images. And then there's an equivalent view on that as well. So we have a feature map, so a function on some domain, and we want to map it to another feature map. And we want to use the same structure as in classical neural networks, so a linear mapping, a linear operator, a bias, and a nonlinearity. And so this is a relatively well-known result, that any linear map which is bounded between such function spaces has to be a kernel operator. So it has to have this form. So this is like the matrix vector multiplication of these feature maps. And we want to put this under equivariance constraints. Okay, so this is summarized in a theorem. So we're looking for a kernel operator or an operator K between two function spaces. And important here is that these functions are defined on homogeneous spaces X and Y. This means that it's a space on which my group can act. And it has to be transitively. Well, first of all, the K should be a kernel operator. That's because of the linear unboundedness. And then if we impose an equivariance constraint, which is formalized here, that actually leads to the fact that my two-argument kernel can be represented as a one-argument kernel, where this argument is transformed by this relative pose vector. And these are correction factors due to the transformation acting on the measures. But in most groups, we can ignore this, and then it becomes a bit more cleaner, of course. So if we then insert this over here in the kernel operator, we actually obtain a group convolution. Okay. And then finally, I talked about images being, or convolutions being equivariant to rotations only in particular cases. Well, item G basically says if my output space can be treated as a quotient of the main group, like SE2, with some subgroup, rotations, for example, then this puts a constraint on the kernel. And in this case, it says that the kernel has to be isotropic or symmetric with respect to the subgroup acting on the position space. So yeah, okay, that's again summarized over here. Okay, so in summary, so if we consider roto-translations and we want our operator to be roto-translationally equivariant, but want to stick working with 2D images, so from R2 to R2, then this puts the following kernel constraint. So the kernel has to be isotropic. And if we do not want any constraints, then we have to work with group convolutions. So yeah, we've discussed that extensively. Okay, so this brings me to the conclusion. So GCNNs, they naturally arise from neural networks under equivariance constraints. That's what I just showed. And also theoretically motivated, but also experimentally, I showed that GCNNs improve upon classical CNNs by, well, first of all, making data augmentations obsolete if these transformations are included in a group. No valuable network capacity needs to be spent on learning geometric relations because we equip them with such structure. And basically this geometric structure allows to deal with context in the sense of a recognition by components or relative poses viewpoint. And basically with this, we can reach performances that cannot be reached by data augmentation alone. And in many applications, I think this is very important. These GCNNs provide geometric stability to input transformations.